All right, hello everybody. So today we will be dispelling some magic and talking about kernel mode, which is like the core part of the operating system. So first off, bit of housekeeping, make sure you try and log into the GitLab server. You'll be greeted with the nice "your account is pending approval" message, and you won't be able to do anything. I have to run a script so that you actually get access, because anyone on campus can log into it and I don't want them to actually use it. So just bear with me on that. You guys are mostly nocturnal and I am not, so if you don't get access right away, don't worry about it. I am probably asleep. So just let me wake up and I'll run a bit later. Also, by show of hands, how many have some experience with like Git and GitHub and using SSH keys and all that stuff? It's like half, or judging by last class, that's like everyone, but no one wants to put up their hands. So first lab, I'll give some instructions with that. Oh, is that a question? No? Oh, whoops. Lower the screen, down. Sorry, didn't see that. All right, that's better. So, since people are comfortable doing that, that actually should be good. So we'll go with that. So just make sure you log in. Everything's going to be released on Monday. So that will be your first lab. It's probably a bit on the shorter side, which students generally don't complain about, because I'm assuming setup may or may not be awful. But I guess we'll find out. So back to course content. So everyone's kind of had some experience with assembly. In general, there's three major instruction set architectures, or ISAs, used today. And it's just the machine code or just magic numbers that the CPU actually understands. Because at the end of the day, everything is just numbers in computing, and it's just how you interpret them is just the magic. Computers are actually fairly dumb things. So there's x86 64-bit, which is AKA AMD 64, you might see called. They're the same thing. That's like desktop servers, non-Apple laptops, things like that. Then there's AArch 64 or ARM 64, which is like pretty much everyone's phone, tablets, and if you're lucky enough to have one of the newer Apple laptops, that also runs that. And then there's a newer kind of instruction format called RISC-V, aka RV64GC, that is like an open source version of ARM that you could actually implement your CPU on without having to pay ARM like millions of dollars. So that's one way the market's kind of going. People mostly use it for embedded, and it'll probably switch over in schools at some point. Some of the examples I might show are RISC-V, because there's an MIT project that actually implements their own kernel using that. So we'll touch on all of them a bit in this course. Hopefully less x86, because it's really, really, really ugly. So as part of ugly, this is kind of its permission checks. So they have a concept called rings to control instruction accesses. And each instruction, so like each assembly instruction, belongs to a certain ring of permission where you are allowed to use it. And all the rings are like complete subs or supersets of each other. So if you're using the kernel ring, you can access everything in the rings above you, so you can access all user mode instructions. But if you're in this kernel ring 0 here, you can't access anything in hypervisor mode. So these are the three modes. There's generally a hypervisor mode. On x86, it's called ring -1, which is why one of the reasons why x86 is pretty awful. And we won't touch hypervisor mode till the end of the course, so don't worry about it. Then the next is kernel mode. So kernel mode is ring 0, and those are the CPU instructions that can actually interact directly with hardware. And there's a separation that the kernel of the operating system is the only thing allowed to touch hardware, and your normal applications aren't allowed to do anything with it. And it does this by running the actual processor in a different mode that just doesn't have access to the instructions. So far, you've been using user mode, which is ring 3, and you might question why ring 1 and 2 don't exist. And the answer to that is it's x86, don't worry about it. So, which is a stupid answer, but it is how it is. So user mode is like all your applications you've been running so far in your life. You can't touch hardware directly. You have to go through the kernel, even though you may not have known the name of it before. But you can't touch hardware directly. Something does it for you on your behalf, which you might have thought was the operating system before, but more technically, it's the kernel. And we'll see that boundary really, really up close and personal today. So you can think of it as like, yeah, this hard boundary where there's something called user space. So that's all of your normal applications that just run in user mode, hence the name user space. It's kind of a good name. And then there's kernel space, which is the code that runs in kernel mode that can interact directly with hardware. And you so far have not been allowed to use it or even probably know about it now, but now you get a chance to. So there are these things called system calls to transition between user mode and kernel mode, which is what you have been using, even though you might not have known it. So funnily enough, you can think of them as kind of like C functions if you want, and you can think of the kernel as a big library if you want to make things easier. And amazingly, the whole kernel only has 451 functions at the time of this lecture. And that's it. That's all your programs can ever do to interact with hardware, which is pretty amazing that the Linux kernel survived like, how old is it now? Like 30, 40 years. And it only has 451 calls that do everything. So we'll get a taste of those calls today. So yeah, we'll get a taste of those calls today. So as a quick aside, so there's a difference between an API and an ABI. So an API just is like a high-level description of something, and an ABI is like the nuts and bolts details, like when you were writing assembly, exactly how to pass your arguments and everything like that is part of the ABI. So like the first argument should go on the stack, or the first argument should go in a register, or something like that. So that describing that as part of the ABI. An API is much more general. It's like, hey, I have a function that just takes 2 arguments. I don't tell you where they are. It's just like, yeah, it takes an X and a Y, and it does something and gives you a number back. So that abstract, just a description of like inputs and outputs, and just being very general about it is an API. And then an ABI specifies exactly how to lay out that data and how to like concretely communicate with it. So like that same function, so a function that takes 2 arguments using the C calling convention. So that's one of the nice things your compiler does, is if you give a function with arguments, it will make sure that generally they're passed on the stack and they're specified in an order, because you know stacks could grow up, they could grow down. The stack pointer could point at an empty element, it could not. So all of that is defined in the C calling convention, and that's all done for you by the compiler, so you don't have to worry about it. So till now, you haven't really had to deal with an ABI. But that's an important distinction we'll see later in the course when we get to libraries. But it's good to know that API, high-level description, ABI, like nuts and bolts details on that CPU, like what exactly goes where. So doing that, this is the system call ABI for a Linux on like an ARM64 machine. So unlike assembly, where we were just doing a call instruction or something like that, to do a system call, there's a special instruction called SVC. And SVC just lets the kernel take over and do something. And the ABI between that is it passes arguments in registers. So the machine has a bunch of registers. It only uses, 7 for system calls. So in the X8 register, the number that's there specifies what function to call. So they're just randomly assigned numbers. And then you are allowed to have up to 6 arguments, X0 to X5. So can anyone tell me any limitations of this as an ABI? Yeah, so your function would use could use all the registers.
Modify the register, and that would overwrite the argument that's being passed.
So the function could overwrite the arguments or registers, do whatever with them, and then they could restore them at the end if they wanted to. That would be part of the ABI, but for now we don't care about that. So like that's caller save and call saved. Yeah.
So what's an SVC instruction?
It's just a special instruction that initiates the kernel to take over and do something. In this case, it would be doing whatever that system call is based off whatever magic number is in X8. So you can think of it as like doing a system call, and it's like equivalent to a call function in assembly. But you don't need an address or anything. It just goes straight to the kernel. Yeah.
Maybe like all arguments are specified to assign to one exact, like one specific register is not fully utilized by three other registers.
Yeah, well, you can't really use other registers, but so I guess another way of thinking about this is how many arguments could my function have using this ABI? 6, right? What if I wanted to make a function with 7 arguments? Yeah.
Put the stuff on the stack pointer.
So yeah, one of the responses, just put the stuff on the stack, but the stack is not part of the ABI, so you wouldn't know how to get the 7th argument because you have no idea where it is because it's not defined. Right? So this is the complete ABI, there's nothing else. So this means that I can't have a function or a system call with 7 arguments because I didn't define a 7th argument. You don't know where they are. And also, all my arguments are exactly the size of a register. So what about if I wanted to pass, I don't know, like a 128-bit number? Well, I can't. I'm assuming like a 64-bit CPU, so all my registers are 64-bit. And if I wanted to pass an argument as a smaller value, that's like, I don't know, 4 bytes or something, then I'm wasting half the register because I have to use a register and the rest of it would just be wasted space. So, yeah.
So we can't find the stack, or there is no stack?
So the stack would exist, but it's not defined as part of the ABI, so it doesn't use it at all. Yeah. Yeah, so it would be possible to find more argument, but then you have to change the ABI, and then everyone has to agree, because this would be like compiled into your code, and like the golden rule of kernel development is you never change the ABI. So as soon as you set this, you have to follow it until the end of time, which is like why Windows and stuff like that has a lot of weird old edge cases. It's because as soon as they implement something, they can never undo it because someone that pays them will have their software break and they will get very, very angry. So this is like the full ABI. You can assume it saves the rest of the registers and doesn't touch them, but this would be the full ABI for Linux. So if we could pass more arguments if we wanted to, like one of them could be a pointer, and then we could say, hey, that points to something that has a lot more space. But in general, this is how you do system call interfaces. There are other ways around it. So we can represent these system calls just like regular C functions, except we know that the arguments are actually going to be passed in registers, and it's not going to use like a C assembly call. It's going to translate it to something like we saw before. So for example, if we have a write system call that takes so it writes bytes to a file descriptor. So its API, its high level description, is it has 3 arguments. First one is FD, which is just a file descriptor to write bytes to, which is just a number. And then an address of a contiguous sequence of bytes, so a buffer. And then a count of how many bytes to write from the sequence. And then they all have types. So the type of file descriptor is int FD, so it's just a normal int. Then const void star is just a fancy way of C saying it's a pointer to something. I don't care what it is. Don't worry about it. It's just a pointer. And then size t is just an unsigned integer that is as big as the architecture. So it's an unsigned 64-bit number. And then S size is a signed version of that. So it's a signed 64-bit number, so it could be negative. And then there's this exit group system call that takes one argument, the int status, and it's just the exit code for running the status. And as soon as you call this, whatever program is running is now exited, it's dead, everything associated with it is now gone. And so the exit code, you'll see that the type's an int, but it says the exit code is only valid for 0 to 255. And that's because it's defined that it just chops off the rest of the number and truncates it, and whatever the lowest byte is the return value. So you may have seen the return value for that, or when you run some applications, so that's where it comes from. So I left you off with this teaser, this 168-byte program, which is actually prints hello world, and those two system calls I introduced are exactly what this uses. So everything on every binary file is just some binary format, and everyone just happens to agree on it, and otherwise it's like fairly magical. So for example, the magic to an ELF file, so ELF stands for executable and linkable format, ELF. So that's just a file format, and it describes an executable program. So any ELF file will start with 4 bytes. What we kind of saw before, we saw 7F followed by the ASCII ELF, all in capital letters. And then if you dive into the file format, there's some bytes after that that signifies, you know, if it's a 32-bit or 64-bit machine, if it's little endian or big endian. And most file formats follow the same thing. Everything just has some magical numbers on it, and that's how you know what the file is. And to show that I am not lying, so we kind of saw it before, that before when we wrote, you know, our read first 4 bytes program. So when we wrote that program, we, you know, played around with stuff. We figured out that that our HelloWorld program, you know, it started with ELF, so it's an executable file. But funnily enough, so does pretty much everything else. So even like libc, so the C library, that's just an ELF file as well. And pretty much every other file follows the same magic thing, but just the magic numbers happen to be different. So for example, where is it? User share. This cat. So like JPEG files, they always start with those 4 bytes. And spoiler alert, the only way your computer knows what a JPEG file is it just reads those 4 bytes. And if they are exactly this, it knows it's a JPEG file. And that's like the magic, yeah.
Can you do bad stuff to a computer by making it think that it's a specific file format and then making it like treat as a specific file format and kind of hack into it?
Yeah, the question is, can I just like say it's a specific format and then format it badly and then do some fun hacky stuff? And yeah, of course, that's like a whole category of exploits. So if you're writing a program that uses JPEG files, well, you have to write it so that it can handle invalid files and hopefully just throw them out. But reading invalid files wrongly is all sorts of hacks you can do. So that's like sending, what was it, like if you sent a specific crafted JPEG file to like an iPhone before, you could get access to the entire phone. So of course you can do things like that. Yeah. So endian is like how multi-byte numbers are formatted. So like everything is byte addressable, right? But if I have like a 4-byte number, well, is the 0th byte like the largest part of that number or the smallest part of that number? And endian just says, oh, it's the most significant byte or the least significant byte. So it's just the order. But everything we have is little endian. And yeah, so was it baseball? And yeah, PNG, same thing, just has a magic byte at the top, and their magic number has the letters PNG in it. But this is magic you'll see everywhere. So sorry I dispelled that, but like all file formats follow this. It's actually called a magic code, and that's the illusion for everything. So like Mac OS will have that. Their magic code on a 32-bit machine is like the binary. If you read it out in hex, it says feed face, and their 64-bit is feed face of. So everyone does that. It's a very common thing to do. So if you want to read more about the file format, you can use this ReadELF. So it will read everything about that file format. We'll skip a bit of it for now. Basically, it contains like a header file, and none of this is really important. It's more to show you that there's actually no magic here. So there's like a header file that contains that information about the machine. So what specific architecture should this program run on, and where's the entry point of it. And the entry point is where the kernel will start executing code for that, and that's it. And it doesn't correspond to your main function if you compile something with C. And then it takes like something called program headers that are required for executables and section headers required for libraries. We don't need to know about either of them. Just know that this like minimal example will just have one program header that says, hey, there's some executable code here. So let's go ahead and look at that. So if we just do ReadELF on our small file, we can see some information about it. So it says, hey, it's little endian, it has a version number, it has an OS ABI, so that's where that ABI comes from, so it's defined there. So it's saying that, hey, I run on Unix, and I use that ABI, so it knows to expect system calls to happen in a certain way. And then it has a version. Generally, you don't touch this because you never touch the ABI or you're going to break literally everything. And then the type, the machine it runs on. So this is an ARM64 CPU, and then version. And then here we have an entry point that you actually specify. And then later it says, hey, the size of this header is 64 bytes, and the size of all the program headers are 56 bytes. So those are the two things we need in our ELF file. So just right there, that's 120 bytes of our 168. So like 71% of this file is just completely wasted just in describing the file. So other than that, this is the program header. And basically all it does is say, hey, load this entire file, which so A8 is 168. It just says, load this entire file into memory, and then you get to say what address you want that whole file loaded into memory at. So here, I just say, load the entire file into address 10,000. Why 10,000? Because I felt like it. You can literally say any number you want, except for 0. You can't say 0. But other than that, you can say whatever number you want. So all I say is load everything starting at address 10,000, and that's the 168 bytes. And then I say start execution at 78. 78 in hex is 120, so that just says the first byte after the header files. And again, this is like way too much detail than you need to know. So if I have that, my header files, my information about it, waste some space, and then the next 36 bytes are instructions, and then we have 12 bytes for the actual string hello world. So here, just adding instruction start at 78, which is 120 in decimal. So that was our starting address, so it just says start executing this instruction. And then this is the address of the string. So it's like 10,000 9C, because 9C is 156. So that's all hello world is. So this is the actual important part of the lecture, is this strace program. So this is really, really helpful when you do all the labs, and not even just the labs, in general. So there's this system call interface, and literally every program has to pass through this interface. So strace will tell you all of the system calls that actually occur. So we can go ahead and play with that for a little bit then. So if I use strace, whoops. So if I use strace on my program I had before, I see all of the system calls it makes and even some it doesn't make. And so first it starts with this exec VE. So we'll get into that later in the course. That's basically someone else called this, and that's how you execute a program. So something else executed this HelloWorld program for me, so I can thank them. And then here it has a write system call. So it writes to this magic number 1 and writes the string hello world with a new line and writes 12 bytes of it. So 12 bytes is hello, that's 5, space, 6, world, that gets us to 11 bytes, and then a new line, which is a single byte, so that's just 12 bytes. And then we see the actual hello world and a new line, which kind of looks ugly, that these two outputs are getting mixed together. So you'll learn this later in the course, but I can unmix them together and do something like that, so it just looks clearer. So here is my write call. I write hello world, and I write 12 bytes. So it returns how many bytes actually get written to. And then I call exit group with 0, and then my program's done. So all my hello world does is make 2 system calls. Yep.
So does this mean that this file cannot be run on a Windows machine because it does not have the right ISA?
Yeah, so the question is, does that mean this file can't be run on Windows because it doesn't have the right ASA? And yeah, it won't. So if you have a virtual machine, you could run it because you'd be running Linux, but anything else won't run this. So I even have another file here that's the exact same thing. So it's for Linux, but it's for x86, so it's for a different ISA, which would have a different, it has different machine code, and it would have a different ABI. So if I try to execute that, it says exec format error because that's not what this machine is. So if you download the examples thing and you're actually running it on like AMD or a more normal CPU, you can actually run that one, but not the other one that I just ran. So that's why there's 2 versions of it, because now they're specific and I can't transfer it. I can't run that on Mac. I can't do it on anything. I have to use Linux, and I have to use whatever the actual ISA is. Okay, so there's just a little bit of magic here, which is I write to just this magic number 1. Everyone's used like printf. Has everyone heard of like standard error, standard out before? Yeah, thumbs up, okay. So those are just magic predefined numbers, and on Linux, they're just certain file descriptors. So you just memorize them, and we'll see them later, but like file descriptor 0 is standard input, file descriptor 1 is standard output, file descriptor 2 is standard error, and that's it. So if I write to file descriptor 1, that's writing to standard out, and I will see it when I execute something. And to show you that I'm not lying and there's no magic going on, let's see. So remember we had this hello world? So now we have this strace utility that tells us all system calls something makes. And because we know that there's user mode and kernel mode, everything that does anything has to pass through this. So we can go ahead and strace hello world, which is our C version of it. So let's go ahead, clean it up a little bit. So if we do that, it's got a lot more crap. But at the end of the day, the last 2 lines, are exactly what we had. There is a write to file descriptor 1 of 12 bytes, and then there's an exit group, and then there's a whole lot of crap above. So this is all the stuff C did, which isn't that bad. So it used some BRK, it has like some nmap. We have some weird things, preload, I don't know what that is. Well, I do, but you don't. Then goes through. And then here we can kind of recognize this. That's the C standard library. So your program, if you compile it in C, one of the things it does is it loads the C standard library, which has to go through the operating system, well, and more specifically, has to go through the kernel, which is part of the operating system. So this we can kind of see here is it's doing something with libc, and open returns a file descriptor, which is just a number. So file descriptor 3 is the standard C library, and we can even see that it reads from 3, and hey, it looks familiar. It says ELF. So we saw before the C standard library is just an ELF file too. Stupidly enough, it's the same like 7F. For some reason, I don't know why, the default output format for binary is an octal. So that's why it looks like this. So if you translate octal to hex, they're the same number. Don't ask me why the default option is octal. I will never know. And then it does a bunch of other crap and does some more stuff, some stack limit, does something probably to protect you from yourself. And then at the end of the day, all it does is it writes our hello world after a bunch of work we didn't really need to do. So just to really show you that, hey, C is not that bad, and this is what anything does no matter what language you run. Well, I have hello world in Python. So hello world in Python, let's clean it up. Well, we'll kind of do the same thing. It has something before, but at the end of the day, it's exit group at the end, and then there is the right hello world. But instead it does, oh gee. Yeah, just wait for it, yep. So it does a lot of stuff. All right, so just for fun, I think I heard it last time, JS. So JavaScript, well, exit group at the very end. And then before that, oh God, I don't even see right. Did I miss it? Is it there?
Right.
It's not.
It's up more. Yeah.
That doesn't look like Hello World. Wait, does the JavaScript one not even work? No, it works. See, more evidence why you should never write anything in JavaScript. Wow, that is the ugliest thing I've ever seen. Okay, so if we can do strace, we can say just give me certain function calls. So I can say strace, just tell me about all the writes. So Java writes to file descriptor 5, it writes a star. What? And then it writes to file descriptor 17, so it opens 17, at least like 17 other files for Hello World. It writes just 0 or 1 and a bunch of zeros, 8, then it does it 12. What the hell is JavaScript doing? So JavaScript does a whole bunch of crap, but somewhere in all of its stuff that it does, there's that write to Hello World, and it actually writes Hello World. But for the love of God, don't use JavaScript. Okay. So if you wanted to like really know about, take those instructions that like 36 bytes and turn it into something you can actually read, like assembly you might read, you could like copy and paste those 36 bytes into a disassembler, and you'd get something like this to see that, hey, it actually matches the ABI. So there, remember X8 was like the register that has the system call number. So all this means is if I put just 64 in it and then later do an SVC instruction, that means I want to write something. So the first argument would be 1, so I want to write to file descriptor 1. And then the second argument, on ARM I have to do it in 2 steps, but just basically makes the address point to the string. And then I say that the count in the third register is equal to 12. That's how many bytes there are. And then this would actually do the system call. So whenever you start executing the next instruction, the kernel would have run and actually printed hello world out for you. And then the next one is I'm setting up a call to exit group. So exit group just wants 5e, or the number 94, in that system call number register, x8, and then I just give it the value 0 and make another system call. So that is the actual assembly of my hello world program. So it just makes 2 system calls, write and exit group, which everything else, that's like the minimum thing you have to do hello world. So the remaining 12 bytes, will, of course, were the string itself. So ASCII encoded, they just look like that, including a new lane. And if you ever have to do like low-level ASCII stuff where you're reading characters, fun little thing you could do is bit 5 tells you whether or not it's a capital or a lowercase letter. So, and they differ by 32 because that's what bit 5 is. So if bit 5 is a 0, it's a capital, and if it's 1, it's a lowercase. So that was an intentional design to make really slow machines actually be able to tell you if something's a capital letter or not really, really fast. So that's a count for every single byte. We saw what C does. So anyone tell me the difference between R string and like normal C strings? Yeah. Yeah, it's not null terminated. So null terminated, that's just a C thing. Strings don't have to be null terminated. In fact, the kernel doesn't want null terminated strings because that write system call just writes bytes, and you don't want to restrict what bytes the user can write. So if I said, hey, write has to have a null terminated string, suddenly I can't write a 0 byte to any file, and that would be why it's a virtual machine. So anything we do to it, if it wrecks it, it's fine. Especially would not let you test your software and like write kernel code on their machines, because if you're writing kernel code, well, you have direct access to. Sorry? Oh, the live stream stopped. On YouTube? Or the Discord one? Oh. Seems to work. What? What died? Okay, I assume it's still alive. I think the stream might have dropped, but I have a recording of it anyways, just in case. So, when you actually write kernel code, it's a bit different in that the kernel is already running. So you can actually inject code into it on demand, and that's something called a module. You can think of it kind of like as a library. So whenever it loads, it would execute some function that you tell it to whenever it gets injected into the kernel, and then execute. We'll see an example, and we'll see an example of it later. But basically, there's no main, there's no nothing. Kernel development's a bit weird, but you have full control over the hardware and everything else running in that machine because you are all powerful. So there's two major types of kernel designs or architecture designs. So we saw before there's this clear user space and kernel space. So there are different architectural designs. So the first one's called a monolithic kernel, which basically runs most of the operating system services in kernel mode directly. So that's anything to do with virtual memory, process scheduling, inter-process communication, like file systems, everything in this course, and device drivers, everything will be running in kernel mode. So nothing is done in user space. kernel mode, just they throw everything in the kitchen sink into it. And the other design is the opposite of that, where you try and put as little code as possible in kernel mode. Because it is all powerful, the more code you have, the more bugs that you could have. So the larger the attack surface is, if someone gets into kernel mode, they get into the whole machine. So one idea is, well, I'll just put as little code there as possible. So it is possible in some designs to move file systems and device drivers and more like advanced types of communication between processes to user space and just have like a minimal set of things in kernel space. But the things that have to be in kernel space are virtual memory, like managing the physical memory, process scheduling, saying what runs when, and basic inter-process communication, because it has to go through something. And then question, if I'm running Parallels, VM Fusion, or UTM, I'm using QEMU, which is basically what UTM uses. So the answer to that is pretty much UTM. But we'll give setup instructions for Windows and Mac for the lab, and hopefully that will work. But I'm setting aside some time for lab 1 of like setup issues just in case, because it'll be new and hopefully more modern. So monolithic kernels and microkernels are kind of the two main architectures, but there's always fuzzy lines depending on who you ask. So like in Windows, some emulation services aren't in kernel mode, they're actually in user mode. At one point, Windows actually had an HTTP server in kernel mode because I don't know why, but that would obviously be a bad idea, because if your web server gets compromised, hey, they have access to everything, which you can tell probably wasn't the greatest idea. But the benefit to having everything in kernel mode is it takes time to do a system call, and it takes more time than a normal function call. So the more system calls you have, the slower your thing is going to be. So if your web server runs really, really slow because it has to go from user to kernel to user to kernel, well, one performance thing you can do is to say, put the whole thing in kernel space and I don't have to worry about it. So, but that's obviously not a good idea for security reasons. And then macOS has device drivers in user mode, but like file system stuff is still in kernel mode. So it just depends on the underlying architecture. There's also like research areas to like try and push the boundaries of microkernels more. And, you know, surprisingly enough, they called them nanokernels and picokernels, as like, you know, never doubt the imagination of a computer scientist. So they just try and push even more and more stuff into user mode instead of being in kernel mode. But that's like research stuff that you might get interested in later. So there's many different types. Real ones are typically messy and don't fit that exact definition. So to wrap up, so the kernel, that's the interface between CPU mode boundaries, and those are hard boundaries. And what we can definitely say is that the kernel is part of the operating system, and past that it gets fuzzy. But the kernel, there's a real nice boundary there. So it's that transition from the CPU being in user mode to kernel mode and what instructions it can access. So clear separation between what's a kernel and what's not a kernel. A little bit fuzzier when you just talk about operating systems in general and what makes an operating system. So code running in kernel mode is part of your kernel. That's an easy definition. And then system calls are that interface between them. And every program, no matter what, has to use that. If it's using Linux, it will use that. So you can strace literally any program you ever write in any language, and you can figure out exactly what it does, because guess what? They're all running on the same kernel, and you get to see what they do. So no matter what language you write in, this course is definitely going to help you, because hey, that's what's actually going on. And then we saw some file formats. Less important, but we saw how to define a simple HelloWorld and like the minimal program we could ever write that takes away all the magic, the difference between an API and an ABI, and most importantly, that strace command. So you really want to know that strace command. And then we just saw different kernel architectures that basically just shifts how much code is in kernel mode. So just remember, I'm pulling for you.